Hello and welcome to this video presentation. My name is Romain Saki. I work as a postdoctoral researcher at the Paul Scherrer Institute in Switzerland. More precisely, I joined the team of Technology Assessment in mid-2019. The Technology Assessment Group specializes in evaluating technologies from an economic, environmental, and social perspective. This presentation is a little bit about life cycle assessment, which is a tool we use a lot at the Technology Assessment Group, but it's a lot more about lifecycle assessment applied to passenger cars. Lifecycle assessment of mobility in general is a strong topic of the Technology Assessment Group for several years now. Therefore, the work I will present is of course the product of several years of work from my colleagues and myself. We have recently experienced an increased exposure of our work to the public, notably through the release of our online calculator tool for passenger cars, and with that came as well a number of questions. Therefore, we hope to be able to answer some of them through this presentation. Now, let's try to first understand what LCA is about. Let us say we would like to know the carbon footprint of washing a kilogram of dirty clothes. Life cycle assessment is first about understanding the economic system in which our washing machine is embedded in. We call that the product system. Hence, we need to first understand its life cycle and consider all of its relevant life cycle phases. A washing machine is made of components that will be made, assembled into a washing machine. The washing machine will be shipped to its market of use using trucks maybe. It will be displayed in a retail store. The consumer will buy it, will use it, and will need electricity for that. It will maintain it every now and then the washing machine will be taken apart, dismantled, and the recyclable fractions will be recycled, maybe, and the non-recyclable fractions will maybe be incinerated. We then understand that the life cycle of our washing machine relies on goods and services supplied by other product systems. For example, as we saw in the early life cycle stage, some transport is needed to ship the components of a washing machine to the assembly plant. Therefore, let's consider as well lorry transportation. Our truck appears to have its own life cycle too. Its components need to be built, assembled, shipped. The trucks need fuel, they need maintenance, roads need to be built, etc. Once we understand this life cycle, we can connect it to the life cycle of our washing machine. But that is not all. We see, for example, that during the use phase of our washing machine, we will need electricity. Therefore, we also need to consider the life cycle of electricity production. Many electricity technologies will provide into the grid. One of them could be wind power. And the life cycle of wind power will also supply electricity back to the manufacturer of the truck as systems are interconnected. There could be also, for example, some web browsing included in the life cycle of a washing machine. Maybe the user at some point will look up someone for repairing the washing machine, or maybe it will look up the washing machine model on the retailer's website. Web browsing will require servers, which would require electricity, and also some electricity will be required to operate the computer at the user's residence. Here again, we see that life cycles interconnect. It is only when we have resolved the whole system that we can pretend to calculate the environmental footprint of our washing machine via the calculation of the carbon footprint of all the services that supply inputs to the life cycle of our washing machine. Let's now have a look to the life cycle assessment of passenger cars. The life cycle would typically include the raw material extraction and energy conversion used to manufacture the components of the car, as well as the assembly of the components into shaping the vehicle. We would also include the shipping of the vehicle to the market, we would also include the energy chain, that is the provision of the energy for fueling the tank or charging the battery. We would also include the manufacture and maintenance of the road and other road infrastructures, the maintenance of the car, and eventually we would include the disposal of the car. That would entail the dismantling of the vehicle into different material fractions and their recycling. We distinguish two main levels of modeling: the foreground model, which includes the modeling of the car and the driving performances and its composition components wise, and the background level, where we would have all the activities that supply different types of goods and services, such as electricity and steel production, aluminum production, and such. The supply of these commodities are associated to environmental footprints, which allows us to calculate the environmental footprint of the vehicle over its lifetime, and we would then normalize these environmental impacts over 1 kilometer to obtain results in terms of vehicle kilometer. This slide shows how greenhouse gas emissions would typically be distributed over the life cycle of a vehicle equipped with an internal combustion engine, such as a gasoline or a diesel car. We would typically notice that about 2/3 of the greenhouse gas emissions occur during the use phase of the vehicle, where the fuel is combusted, leading to emissions of CO2. We would also typically notice that about 13% of the greenhouse gas emissions originate from the manufacture and the assembly of the car components, and another 13% coming from the extraction and the refining of the fuel. The remaining 8% would be dispersed across the various life cycle stages of the vehicle. From a data quality point of view, this has the advantage that most of the impacts are coming from life cycle stage for which we have a rather good documentation, as the fuel economy of different vehicle models is well documented. Now this slide shows the typical life cycle assessment of a battery electric vehicle, which is quite a bit different than that of an internal combustion engine vehicle. Indeed, most of the impacts are actually displaced upstream the supply chain. Because there is no combustion process during the use phase of the vehicle, most of the CO2 is now located at the level of electricity generation, but also quite a good deal for the manufacture of the car components and the battery. From a methodological point of view, this is a bit more complicated because the problem is displaced upstream, where we have less documentation and where the uncertainty level is greater. How do we dimension passenger cars? Well, our model starts by using the skeleton of a car or its chassis, to which it will add a certain number of components such as wheels, braking system, suspension, etc. The sum of the mass of these components and the chassis makes up for what we call the curb mass of the vehicle. Once the curb mass of the vehicle is known, we will size the engine power of the vehicle using a power to mass ratio. We will then size the powertrain of the vehicle as well as its energy storage unit. This can be the fuel tank or a battery, depending on the type of vehicle we're looking at. However, sizing the engine and the energy storage unit will also affect in turn the curb mass of the vehicle. Therefore, we understand that this is an iterative process and it will be repeated until the curb mass of the vehicle converges towards a stable value. Each vehicle in our model is defined by close to 100 different input parameters. Some of these parameters are common to all vehicles, some are technology specific, while others are specific to a given size class. For example, the lifetime of the vehicle, the annual mileage, or even the number of passengers on board are usually parameters common to all vehicles. Other parameters, such as the lifetime of the battery or the lifetime of the fuel cell stack, are parameters specific to battery electric and fuel cell vehicles respectively. And also, the efficiency of the engine will differ across the powertrain technologies. We know, for example, that electric motors are much more efficient than internal combustion engines. And then we have parameters that are specific to a given size class. For example, the aerodynamic drag coefficient will be smaller for small city cars than it is for SUV vehicles. Also, the rate of lightweighting to be expected in the future will be different depending on the size of the chassis. And finally, the size of the battery for battery electric vehicle will differ across size classes. Once that we have properly dimensioned the vehicles, we will calculate their tank-to-wheel energy consumption. To do so, our model will first calculate the total resistance the vehicle experiences along a given driving cycle. This total resistance is the sum of the traction effort, the braking loss, the rolling friction, as well as the aerodynamic drag. This will determine the energy to provide at the wheel. We will then back calculate the energy to provide at the tank or the battery. To do so, we will consider the engine efficiency as well as the efficiency of the transmission line, and in the case of a battery electric car, the battery discharge loss. It is to note also that for electric powertrain and hybrid powertrains, some of the energy consumed can be recuperated during decelerating or downhill sections of the driving cycle. Once the energy to provide at the tank or battery level is known, we will then model the upstream energy chain. For battery electric cars, this means that we need to model the distribution of electricity. This will consider a certain number of losses, such as the charging loss, which can vary whether it is slow or fast charging, the distribution loss, the transformation loss to go from high to medium to low voltage, as well as the conversion efficiency of the power plant. For vehicles that use liquid fuels, we will account for the losses at the fueling station, but also during distribution and refining, and finally the extraction of the raw material. It is to note that for vehicles that use gaseous fuels such as natural gas or hydrogen, the principle remains the same, but we also account for potential slips or leakage during the distribution and also at the fueling station. We can model the upstream distribution of energy for a wide array of fuel types and electricity. For liquid fuels, we of course have conventional fuels such as gasoline and diesel, but we also have biofuels made from crop residues and different types of biomass. And finally, we have synthetic fuels, which are made from hydrogen and synthesized using a Fischer-Tropsch or methanol process. We have gaseous fuels for our compressed gas vehicles. There we can model the supply of natural gas, but also biomethane from different sources of biomass residue, and synthetic gas, which is also made from hydrogen, and the carbon source can come from biomass or direct air capture. We can supply different types of hydrogen as well for the fuel cell vehicles. The hydrogen can come from the steam methane reforming of natural gas or the steam methane reforming of biomethane, as well as from water electrolysis using electricity. And finally, for battery electric vehicles, we have the national production mixes for close to 180 different countries from 2000 to 2050, which of course partly rely on projections. We can also um, model the distribution of electricity coming from a single fossil technology for sensitivity purpose, such as coal, natural gas, oil, nuclear. And finally, we can do the same but for renewable technologies. Synthetic fuels are particularly relevant in today's talks about mobility and sustainability. We try here on this slide to give a brief overview of it. Of course, the simplest form of energy distribution is the direct electrification of mobility. So that basically consists in producing the electricity and distributing it to the charging stations to charge the batteries. It's also the solution that involves the least intermediary and transformation steps. So in many ways, it is the most efficient one. Another route is the route of hydrogen, illustrated here by the blue pathways. So hydrogen can typically be produced by the reforming of natural gas or biogas, or also gasification of woody biomass. That's a process that would also lead to some emission of CO2, which, like the production of electricity, can be stored underground or be used as a feedstock for other processes. Another route to be considered for the production of hydrogen is the water electrolysis. However, this solution is generally a good idea if the electricity the electrolyzers use is from renewable sources, because this process is quite intensive in electricity. The hydrogen is then pressurized to about 350 to 700 bars and then dispatched to the fueling stations. Now, hydrogen can be used instead as an input for the manufacture of liquid or gaseous fuels. And the synthetic process would use hydrogen and CO2 as inputs. The CO2 could originate some industrial sources of emissions, such as a cement plant or a power plant, but it could also come from direct air capture, which consists in removing CO2 from the atmosphere, which is a process that relies itself on electricity. The end result would be a liquid or gaseous fuel that could then be dispatched in conventional um, fueling stations. Now, the solution is promising. The conditions are that it relies on electricity of renewable sources, but its undeniable advantage is that um, the combustion system on the vehicles do not necessarily need a dramatic uh, adaptation to be able to use these fuels. Electricity is of course a very important aspect in our model and in mobility in general, whether it be for charging batteries of battery electric cars or for producing the hydrogen for fuel cell cars, but also for producing synthetic fuels for combustion engine vehicles. Now, the correct electricity mix is important to consider. For example, if we consider a car produced in uh, 2020 and is set to last 10 years, it is important not to consider the electricity mix of 2020 for the country the car is located in, but instead to consider a time-weighted electricity mix over the period 2020 to 2030, which is why it's important to have projections for national electricity mixes. In this way, it allows to integrate the expected development of renewable capacities in the said country. It is also important to correctly account for driving emissions for cars with a combustion system. For CO2 and SO2 emissions, we will calculate those based on the carbon and sulfur content of the fuel respectively. The sulfur content of the fuel will differ across geography and time. For other substances such as ammonia, NOx, methane, hydrocarbons, etc., This is also correlated to the fuel consumption, but also to the emission standard we are looking at, which of course will depend on the production year of the car. We will calculate these emissions for each second of the driving cycle. We will also consider at the first second of the driving cycle cold start emissions. We will also consider running losses as well as evaporation emissions, which are emissions that occur once the driving cycle is completed and you've parked the car. We will further distribute these emissions depending on the environment where they occur, whether they occur in an urban environment or extra-urban or highway environment. Once all the relevant phases of the life cycle of our vehicles are calculated, we will try to compute the energy and material inventories for each of them in regard to our functional unit, which is typically defined as one vehicle over 1 kilometer. We will do so by filling what we call a technology matrix, which is representing the exchange between our different product systems that makes up the life cycle of our vehicle. For example, the seventh column of that matrix represents the car assembly process, and we've put here some random numbers, but it's just to illustrate this slide. For example, that assembly process will need 10 units of steel, 2 units of aluminum, 5 units of electricity, 1 unit of fuel, and it will output 1 car. And then the last column represents the transport activity per kilometer. And this activity will need some fuel, some road, and a fraction of a car, which is basically 1 over the lifetime of the car in kilometers. And this will output 1 vehicle kilometer as a transport activity. Once we have computed the material and energy inventory, we obtain a list of materials and energy associated to 1 vehicle kilometer for all the vehicles we are considering. However, this list as is not very useful because it is hard to interpret and to make the choice of a technology or vehicle type over another one. To do so, we can multiply this inventory by a matrix that contains emission factors per units of products of material and energy. The product of this multiplication will give us how much of each emission is emitted per vehicle kilometer for the different vehicles. Still, a list of emissions is not very useful because it's also very hard to interpret. I mean, should I prioritize a vehicle with the lowest amount of CO2 emitted, or the lowest amount of particulate matters, or the lowest amount of sulfur dioxide? Hard to say. So we could also multiply this list of emissions by a matrix that contains characterization factors for midpoint indicators, denoted here by the matrix C. It will essentially convert our emissions into a list of more easy to interpret indicators like climate change, acidification, smoke formation, human toxicity, eutrophication, etc. We will obtain a number of these environmental indicators, but nevertheless, it could still be difficult to interpret or to make a choice between 2 vehicles. In other words, should I rather prioritize or prefer a vehicle that has a low climate change impact but a high smoke formation impact over a vehicle that has a high climate change impact but a low human toxicity impact? The choice is not easy, which is why we could go a step further and compute endpoint indicators, denoted here by the matrix D, which is a matrix that contains conversion factors to go from midpoint to endpoint indicators. The goal being to end up with a list of usually 3 indicators, which are damage-oriented indicators. So damage to human health, which is usually expressed in DALYs, disability adjusted life years, or in other words, how many years in good health would you lose as a person, ecosystem damage, which is usually quantified as the number of species lost, and resource use, typically quantified in US dollars worth of resource. Um, of course, reducing the number of endpoint indicators down to 3 makes the choice between vehicles easier. Um, but it is not free of subjective choices. For example, how should we value a human life? What is the science between the pathways? How do you link climate change to human health, to ecosystem damage, etc.? After all the necessary calculations are done, we can compute midpoint or endpoint environmental indicators. This slide shows typical results for the midpoint indicator climate change, which we quantify in terms of kilograms of greenhouse gas per vehicle kilometer. Um, the results on these slides are for a car produced in 2020 with a lifetime of 200,000 kilometers, which represents about 15 or 16 years of use, and an annual mileage of about 12,000 kilometers. We have battery electric cars, fuel cell cars, which are electric powertrains. Then we have regular diesel, gasoline, and compressed gas cars, and then we have hybrid powertrains, such as hybrid diesel and gasoline cars, and plug-in hybrid and plug-in hybrid gasoline and plug-in hybrid diesel vehicles, which are like hybrid vehicles, but with the distinction that you can charge the battery. In that case, the battery electric vehicle seems to perform the best, although it is not far off the compressed gas vehicle, which benefits from a rather lean combustion process. Um, the fuel cell car is supplied with hydrogen produced by means of electrolysis, which is very electricity demanding. Here we use an average European electricity mix, which is apparently not decarbonized enough to allow the fuel cell vehicle to be beneficial in terms of greenhouse gas emissions. The combustion-based vehicles are typically characterized by, as we previously mentioned in the first slides, about more than half of their impact coming from the combustion of the fuel. Um, the glider or the chassis of the vehicle is also responsible for a good 13 to 15% of the impact. It is, however, clear that for electric powertrains, whether it be battery electric or fuel cell, much of their performance, at least in terms of greenhouse gas, can depend on the carbon intensity of the electricity mix. On the left panel, we in fact display the performance in terms of greenhouse gas per vehicle kilometer function of the carbon intensity of the electricity mix. We've displayed our reference vehicles, which are petrol, diesel, and natural gas. Their performance pretty much doesn't change regardless of the carbon intensity of the electricity, but the performance of the battery electric fuel cell car and also combustion vehicles using synthetic fuels produced from hydrogen from electrolysis will depend a lot on the carbon intensity. In fact, we can see that battery electric will start to provide CO2 benefits compared to petrol cars starting at 640 grams of CO2 equivalent per kilowatt hour. It will be a bit later compared to natural gas cars, which are a bit better performing. For fuel cell cars using hydrogen from electrolysis, the break-even point occurs a bit later because of the electricity uh, intensity that goes into producing hydrogen. And for synthetic fuels, it occurs even later because you have additional transformation step after producing the hydrogen. Along the lifetime, there is also a break-even point between the battery electric vehicles and the combustion-based vehicles. This is what we're trying to display on the right panel. Um, and this is also very much depending on the carbon intensity of the electricity grid. So we have curves that start at kilometer zero, which basically represents the CO2 to build the car, and from there on, the use phase emissions until we reach kilometer 200,000. Now, the yellow curve that represents the battery electric vehicle um, crosses the petrol vehicle curve with an electricity at 600 grams of greenhouse gas emissions per kilowatt hour after around kilometer 80,000. This break-even point is obviously shortened down to around 40,000 and 30,000 if we use an electricity mix with a carbon intensity of 300 grams and 50 grams of greenhouse gas emissions per kilowatt hour, respectively. And the good news is that you do not really have to worry about all these calculations because we have developed and packaged a tool to do that for you. It is called Calculator, and we have it in two versions as a Python library to do complex calculations and scenario modeling, and as a more accessible online tool with a graphical user interface um, at calculator.psi.ch. Calculator contains vehicles with dimensions that are calibrated against more than 15,000 vehicles. Uh, it offers 9 different powertrain technologies, and we've seen actually most of those: battery, electric, fuel cell, hybrid, plug-in hybrid, and regular combustion powertrains. Um, you can tweak more than 230 parameters to really parameterize the vehicle you want to consider. For battery electric vehicles, but also hydrogen production or synthetic fuel production, um, we have the national electricity mixes of more than 180 countries from the year 2000 to 2050. We have 7 size categories: city car, small cars, lower medium, medium, large, SUV, and vans. You can calculate the fuel consumption against 11 different driving cycles that are more specific to urban environment, or others to countryside, or a mix of both, or highway even. For battery electric cars, we have different chemistries for lithium-ion batteries, and we are able to conduct this analysis, or at least the tool is able to conduct this analysis for you for any time between year 2000 and 2050. So we warmly encourage you to try maybe first Calculator online, and if you have questions that are left unanswered, maybe try yourself at the Python library. All the work that has been presented through these slides is the results of several years of work by my colleagues mostly, and a little bit by myself, which we are listing here on this slide. If you are to use the Python library or produce any results with Calculator online, we would be very grateful if you could cite the tool in your work. Thank you very much for staying with us up to this point. And if you have any questions, you're more than welcome to write to me, and we'll be glad to help you and answer any questions you may have. Thank you.